This video we're learning about geometric series. So much like geometric sequences, they have a common multiple to get to the next term, and we're going to be adding all these terms together. And again, we have a formula for the general term. We also have a formula for sort of if you go out to infinity and have infinitely many terms. So there's a lot of sort of like paradoxical stuff that pops up in here. It's a little bit weird. But we'll go through some simple examples first. So the first thing we're going to do is find this sum up to 12 terms. So we're going to use our formula here. They're basically the same formula. So Sn is T1, and then you times it by r to the n take 1, all over r take 1. So we need to figure out what all these bits are. T1 is 2, R is going to be, well, 2 times 3 gives you 6, and then it's timesing by 3 each time. That's pretty much all we need. So, and then N is going to be 12, because we're looking at the first 12 terms. So this is 2 times 3 to the 12, take 1, over 3, take 1. So essentially, this just gives us 2 times 3 to the 12, take 1, over 2, or if you like, that's just 3 to the 12 take 1. So we can work out what that is. 3 to the power of 12, and we take away 1. Let's try that a bit better. Take away 1. We get 531440. Great, so that's our value there. Okay, so find the formula for the first n terms of this series. So it's a little bit weird. Basically, let's step it out again. T1 is 9, R is minus a third, and then N is just N. So T1, R to the N take 1, over R take 1 is our general form. And then we can plug in all these bits and pieces. So Sn is going to be 9 times minus a third to the power of n take 1 over minus a third take 1. So that's sort of your general formula there. All right, next thing we're going to do here is find the value of this. And we have basically a formula. So S is T1 over 1 take R. But let's see if we can just map out what this is. You can imagine like the best way to visualize this is you have like a square, at least the best square I can draw. And then we're going to use up a half of that square. And then we're going to add on a quarter of that square. Then we're going to add on an eighth of that square, and then a 16th of that square, and then a 32nd, and then a 64th, and then a 128th, and then a 1/256 of the square, and then a 1/512th, and then a 1/1024th. You can sort of see that this whole square is going to get used up almost exactly. You just have to go infinitely deep, because the further you go into your square, the more you have to like subdivide it and do more. I said this was going to get a bit paradoxy, but we're expecting the answer to be 1. And you can actually sort of verify this. So let's do this on our calculator, and I can show you how to do summation notation here. So essentially you get this little symbol here. So I'm going to go x equals 1 all the way up to, let's just do, I don't know, 5 or something. And then inside the summation, we're going to put 1 over 2 to the power of whatever our x value is. And that gives us this number here. But what we can do is we can just keep bumping that up. So if instead of going up to 5, I go up to 15, let's say, then you get 0.999999. And if I want to go up to 215, then you're basically just going to get 1. Not exactly, your calculator is rounding that, but you just got to be real careful. So we're going to use our general formula here. S equals T1 over 1 take R. Now it's really important, this S formula here only works if your series is something called convergent. So convergent is a finite sum, and divergent is not. So I can give you a really good example of a divergent series after as well. But let's just work with this convergent series. So T1 is, let's see, I'm going to be really careful here, a half over 1 take, and R is a half because we're halving it each time. So you get a half over a half, which is a 1. Now, here's a really good example of a divergent series. You take this one, 1 plus 2 plus 4 plus 8 plus 16 plus 32. This is geometric, and it's divergent. Because you can imagine if you just keep adding this up, it's going to blow up and get really big. The other really interesting series to talk about is this one. It's called the harmonic series. Now, this one's a bit weird. This is it geometric? Well, we'd have to check if it's a common ratio. So there you times by a half, and there you would times by, well, I don't know what it is, but it's not a half. So it is not geometric. And it turns out that this series is actually divergent. It's a bit weird. So the harmonic series is really cool. It's sort of a divergent series, but it's about as close as something can possibly get to not being divergent, but it is divergent. So let's check this out. X equals 1 to 10, and we're now just going to go 1 over x, not 1 over x squared. And you get this number, 2.92. So let's try it up to 100. You get this number, which is 5.187. And if it was going to be convergent, we'd be hitting a particular number here. But you can see no matter how high I go, it just does keep getting bigger and bigger. It gets bigger and bigger incredibly slowly, but it does keep growing. You can see if I got to 100,000, your calculator is going to chug for a little while, but it should eventually spit out a proper number, which is kind of big. It's still having a good think about that. Adding fractions is obviously not something your calculator enjoys very much. Maybe I've asked too much of it, but we'll see. So 7.48 was sort of the answer we got before, and going up to 100,000. I might just leave that to think for a little while, but it should be a number that's a lot bigger than 7.48. So there's a really cool proof of why this is divergent, actually. So essentially what you can do to prove this is you can keep pairing them up in such a way that you get a whole bunch of halves. So this bit here, the 1 over 1, we're basically going to ignore that. But I might actually write out a few more terms, and we'll see. All right. So basically what you need to do is you need to pair them up. So that there equals a half. Now, if we look at a third plus a third is definitely bigger than a quarter. So this whole thing is bigger than a quarter plus a quarter. So it is bigger than a half. So if we want to go here, we got a half plus, and we're going to do the same trick here. This is bigger than an eighth. That is bigger than an eighth. That's a 6 is bigger than an eighth. A 7th is bigger than an eighth. And an eighth is equal to an eighth. What happens when you add up all those? You get an eighth plus an eighth plus an eighth plus an eighth, which is a half. Oh my goodness. So again, you get another plus a half. Then to get this next term, you would use this, and then like a ninth is bigger than a 16th, and then you would do that 8 times, which is a half. And you can see that you can keep grouping these up and getting a half, a half, a half, a half, a half. So this series is greater than a half plus a half plus a half forever. And that is a divergent series. So that means this series has to be divergent. So yeah, we won't see too much of this harmonic series because it's not a geometric series. But just be aware that that's something like kind of cool that people will talk about when they talk about series. Let's see if the calculator's finished. 12, good, yeah. So you can see it's blowing up and getting much bigger.